discussion. We have been able to look at multiple regression model. We've been able to estimate it. We've been able to even interpret the results. We've seen the beautiful ways of getting some of the results. And after getting the results, we have interpreted them. Have we done the interpretation? I'm sure you remember the interpretation. We looked at whether a particular coefficient is significant or is not significant by looking at the p-value. Do you all remember?
Yes, please.
Yes, no,
Okay. We also were able to determine whether the coefficients are jointly significant or not. What do we normally use to test for the joint significance? What do we use to test for the joint significance?
So we use all the variances for the independent variable.
No. There's a specific statistic we use for the joint significant testing.
The F statistic.
We use the F stars. What do we use to determine the reliability of the regression model? What do we use to determine the reliability of the regression model?
The R square.
So the R squared.
When is the need for the use of the adjusted R square? When is the need for the use of the adjusted R square? The way you guys are just talking by heart, without raising your hand, it will happen that somebody will now know and everybody will be talking. What do we use to determine the reliability? What is the use of the adjusted? Joseph?
Prof, you use the R squared when you have other variables, unrealistic variables in your data set.
To do what? You use it to do what?
To check how robust your model is.
No, we are not using it to check robustness. And I asked you to tell me the details of that robustness. You can't tell me. So don't use the word when you don't know what it means.
So to test the reliability. So, Prof, Doc, what my understanding is that you use the R squared when there are unnecessary parameters or unnecessary variables in your model.
Why are you using them? Why are you using it when they are unnecessary variables?
You criticize this model. You should have use the actual.
All right. We're answering these things in the exam, so don't worry. Let's move on to other things. You should learn how to interpret the difference between a numerical variable and that of a categorical variable. You should know the distinguishing difference between the two, both numerical variable and that of the categorical variable. And you should always identify all the elements, not just saying that holding other factors constant. You got to mention all the factors properly so that it becomes precise. Okay. And when models are given to you, like to see on your screen, you should be able to identify the meaning of model 1 and that of model 2 and that of model 3. What separates them from each other? You should be able to distinguish them. Okay. Now, we indicated that there are other measures for evaluating the reliability of the model. One of them is the R square. But we also have the mean squared error, the root mean square error, the mean absolute error, and then the mean absolute percentage error. So those ones are here. They all do similar things. that we have already indicated. We have learned how to specify the regression model and how to write the estimated regression equation. What is the difference? We have learned how to specify the regression model and estimate the equation. What's the difference between the model and the equation? Emily.
Okay, so when we are specifying the model, we use beta naught and then we also add the error term. But when we are estimating, we use the actual numbers for the betas and then the error term doesn't come anymore.
Perfect. Now, which one do we use to determine or predict? Is it the specified model or the estimated regression equation? Which one do we use to predict the target variable, predict the dependent variable? Which one do we use to do that prediction? Joseph.
We use the estimated.
Okay. So let's look at some things. I don't think we did. I think we did prediction the last time, didn't we?
Yes, Doc, we did some examples. We worked out some examples.
Very good. So we've done prediction, and now we are in the process of looking at regression diagnostics. Regression diagnostics. So regression diagnosis basically looks like after you've done your entire model and you've gotten the results, you got to be sure that your results are good. And so there are certain things you should check authors whose papers you are reviewing. You got to check whether they've actually taken into consideration some diagnostics. Have they checked for normality? Have they checked for linearity? Have they checked for heteroscedasticity or homoscedasticity? Have they done something to indicate that they are correcting multicollinearity? Have they done anything to determine whether they are correcting endogeneity, autocorrelation, independence, or they have something they've done to indicate model specifications or anything? Or they just give the results out? Those are the problems in most of the papers I've given you that you should correct. You should find out. In fact, many of them omit these important things. But to actually go ahead and use OLS regression and not check for these things is an anomaly, a big one. So let's look at one of the first things you should check after you've estimated a regression model. What is the first thing you should check? One thing you should check is whether there is high multicollinearity. What is multicollinearity? I gave the definition some time ago. Let me see whether someone will remember. What is multicollinearity? Okay, know the definition of multicollinearity. Now, because multicollinearity has to do with multiple independent variables, it is very important to recognize a system of detecting. Because if multicollinearity exists, even though you have a big R square, the beta parameters can still be unbiased. Because the beta parameters may not be a true reflection. The variances can be big because the standard errors can be big. And if you look at the way to get the T statistic, the T statistic is obtained by, look at it, the beta 1 cap minus the beta 1. That is the unbiased beta minus the true beta divided by the square root of the variance, which is a standard error. So if you have a problem with the variances, you will have a problem with the standard error. And if you have a problem with the standard error, you will have a problem with the T value or the T statistic, which will then affect the P value. And that's why it's important to not joke with multicollinearity. So let's remind ourselves of the Brukutu venture, the correlation matrix that we had. This was a correlation matrix. Here I've used the coded variables. So towards the end, all the categorical dummies have been coded. So the code is for that. So the independent variables are many. Now, on the basis of this, multicollinearity exists when you are not looking at the dependent variables. So this column is not important. The column that is important are these ones. These ones are the columns you are looking at. You're looking at those that have got high coefficients, such as what? One of the coefficients is this one, OTR and P. Another coefficient that is high is C and P. And another coefficient that is high is M and RM. So these coefficients are quite high, and you have to check whether they exhibit multicollinearity. Well, to check for the existence of multicollinearity, you got to go back and use something known as the variance inflation factor. It tells you how inflated the variances of the regression estimates are because of the multicollinearity. In other words, it tells you whether two independent variables have a high correlation coefficient. And that high correlation coefficient is making one of them redundant. So the question of whether to tolerate that one or not to tolerate that one is an issue. Variance inflation factor would check the R-squared value for only that particular variable. So suppose that variable is the only variable in the model. That's the only independent variable. It's like we've come back to a simple regression. What will be the R-square? Then when you get an R-square for that one, you come and substitute and you can calculate the variance inflation factor for that particular variable alone. Once you've got the variance inflation factor, you take the reciprocal of that, and that will give you the tolerance factor. Now, how do you interpret them when you have these scores? Well, it's a very simple thing. Once you have the scores for each independent variable, once the variance inflation factor is 1, it means that that particular independent factor has no correlation with the others. It's 1. But if it's bigger than 5, there is moderate multi-co problem. If it's bigger than 10, there is a severe multi-co problem. Let me ask you a question. What do you think will be the variance inflation factor in a simple regression? In a simple regression model, what would you think is the variance inflation factor? What would be the value of the variance inflation factor? Should we have, that's Emily?
Okay, Doc, it's going to be 1 because simple regression has only one independent variable. So there won't be any correlation with another independent variable.
That's it. So these reasonings are some of the things I ask in the exam, not very technical questions. Okay, very simple questions, but it requires the person to ponder. Okay. So let's go back here and look at if we are to run the multiple regression that we had before, and then we are to run that and to check for the variance inflation factor. We should be able to get, I think I had for the actual Brukutu data set. Let me see what let me see whether I can get there. My R square is not opening. My Brukutu data set, for some reason, anytime I call for it, it's trying to joke. Okay, let's see something. You can run that code. You can later run that code. Okay, so let's continue. So when you use a library package and use this car, and then you run this code, it's going to give you some things. For example, this last code would tell you to drop the independent variable whose VIF is greater than 10. And it will do that. This one will tell you to drop the independent variables which are greater than 10. And if they are problematic, it will tell you. And this is a result you get. Now, there are some few things you want to take note. First of all, you will see that the price will get its VIF or its GVIF. It's a similar thing. And in the case of, we use the VIF. In the case of price, the GVIF, you see that it is 24.15. Complement is 10.38. Income is 10.81. We don't look at the location, occupation, and the religion. And who can tell me why we don't look at them? Why we don't check the VIF for these dummy variables? Why don't we need to consider the VIF for the dummies? Joseph.
Because their values have no effect on the model.
Why? How do you know that? How do you know? Why don't we stop Googling? Why don't you consider the VIF for
Doc, I'm not Googling.
variables? Not you. Those that are not talking. Okay, go and find out. Go and find out a lot because it's in the notes actually. Okay. Check it. But how do you solve the problem? So you check those that have got a high VIF like price. What if that price is your main variable? Never be tempted to drop an independent variable because it has a very high VIF. Okay. That's the first thing. Never be tempted to drop it. So what should you do? What you should do is to remove it and check whether the regression model is destroyed. So you remove it and check whether the new R square you're going to get without that variable, the R square is going to reduce significantly. And if it's going to reduce significantly, then you check the coefficient of the other variables. Are they now looking better? If they are not looking good, then it means that the variable being in the model doesn't bother them. But if some variables are actually, insignificant, but now they become significant, then it means that the removal of this particular independent variable is good. So you always remove it, you rebuild the model, you check for the p-values and the R-squares. And then you can use that to determine whether the dropping of this variable can be proceeded. Other than that, you keep them in the model, particularly when you have a theoretical backing for that. The key point is that when you're checking these papers, ensure whether the author actually generated variance inflation factor or spoke about it at all as a way by which, or tolerance factor as a way by which he checked for multicollinearity. If the author is silent about that, that is one thing you want to take note. Now, there is another way you can also generate some things to handle multicollinearity. Yes, Joseph.
Doc, please, I want to find out if you say in the case of multicollinearity and you have your major variable showing multicollinearity, you don't take it out, but you reset the model, remove it, and check the effect. And if it doesn't reduce significantly, I just want to find out if we say reduce significantly, by what fraction or a ratio do we consider as being significant reduction?
So you put in the model, you remove this variable, You ran the model, the R square was 90% before. Now the R square is 50% without this variable.
Okay.
Which means that this variable was helping the R square to be big, isn't it?
Yes, please.
Which means you should keep it. But you check the p-value for the other variables. And then previously, a variable like complement, price, and income were insignificant. But now that you remove this variable, they are significant. Which means that it is this variable that was causing them to be insignificant. So in practical sense, this variable's presence is hampering them.
Thank you, Doc. Thank you, Doc.
So that's what I mean by you look at it, its power, significant power. Any other question? All right, let's look at the next thing. So these are the things you can do. How do you handle it? Remove one or more of the multicollinear variables and rerun the model. We said that. 2, combine some of the predictors. So maybe you're looking at experience and you're also looking at education. And then they both affect salaries. And so you realize that experience and education are highly multicollinear. So instead of using both of them, you combine them. Okay, or you subtract one from the other. Whichever justification you can have, you do one of them to just put these two together. And once you do that, you're good to fly. Please, does that make sense? Then sometimes this combination is known as principal component analysis. Principal component analysis is where some variables are too many, and so you try to combine some of them together. That's PCA. Sometimes by combining the PCA will have loadings, and you will use the loadings to combine them. And that means you are creating a new variable from the existing variable. So if the existing variable was x1 and x2, and then the values were 2 and then 10, 6 and then 4, and all of that. Now you get a new variable. Let's say we call it like A. And this new variable will have some factors because the 2 here will be multiplying some weight. And then the 10 will also be multiplying some weight. These weights are the loadings. Then you now add them together with their weight, and now you get a new variable, say 6.5. It is this 6.5 you are now going to use as a new independent variable and come out with a new regression model. That means you have combined them and used it. Sometimes you use something called partial least squares. You can decide that you will not even do anything, touch anything. You just go and use a different model, okay? And the different model you can use here is the ridge regression. So the ridge regression doesn't matter whether you are having multi-co or not. Please, these are called regularization methods. Take note of them seriously. You meet them somewhere. The regularization methods are used to run the entire regression model, and they automatically handle nonlinearity and multicollinearity. And one of them is a lasso, the ridge, and the elastic net regressions. These will help handle the multi-co for you in the model. So you should know how to address them. So sometimes some people will have the first model as OLS, then the second one as ridge, then the third one as lasso, the fourth one is elastic net and things. Of course, you can't run ridge and lasso and elastic neck at the same time. So you just have to cancel the elastic neck and just do the ridge and lasso and then compare it with the OLS. And how do you compare? There are several evaluation metrics you can use to compare. We looked at some. Some of them is looking at the R square. Some of them is looking at the MI, the minimum absolute error, the MAPE, okay, and so forth. Can use all of these to check which of them is the best model to use. Okay, but you see that if there is multicollinearity in the model, the region lasso will solve that. So it is important to always check for multicollinearity. This is called diagnosis. Another thing you got to diagnose is whether the expected value of the error term is truly equal to 0. Yes, Ima.
Look, so with the VIF, sometimes the output gives you individual VIFs for the specific questions you ask under the construct. So if, for example, if I want to check on price, the specific questions I ask on price, I get individual VIFs for that. Do I apply the same method? That if the VIF is high, I just remove it and then rerun to see if it has influence, or with that, I can just drop the individual question under it.
Sorry, say that again.
So I was asking that in some instances, you run the VIF and you get specific VIFs for the individual questions you ask. So for example, if I have a construct like price and I ask about 5 questions to measure price, I'm able to get VIFs for individual questions like that. And I'm asking if the VIF for one particular question, say question 3 under price, is very high, do I set it aside and rerun the model again, like you were saying, or with that instance, I can just drop it and still keep the construct there as price? Hello, Doc. Hello, Doc.
Sorry, I was talking. I didn't know that I've muted myself. I was saying, yes, you should check and rerun again. You should check and rerun again and be sure. Yeah. The next thing to do is to diagnose whether the errors are truly 0. The mean of the errors is truly 0. And you can use this command, mean of the residuals of the name of the model, check whether it's 0. In fact, when you check our own, you will see that it is truly 0, approximately 0. And when it is close to 0, it means that you have satisfied that particular assumption. So the assumption of normality of the errors, or the mean of the errors equal to 0, then becomes satisfied. Now check whether the papers you're reading are doing that. Another thing is to determine the normality of the errors, whether the errors are normally distributed or are not normally distributed. Now, what do we mean when we say the errors are normally distributed? Well, as the name sounds, you got to check whether they are normally distributed. There are multiple graphs you can use for this. There's even one particular command that will generate the normality for all. But you can use the PP plot. You can use the QQ plot, the quantile normal probability plot. You can use the histogram and current density plot. You are plotting the residuals. But you got to not only rely on the plot, but also check statistically using the Shapiro-Wilk test of normality. There's also the Kolmogorov-Smirnov test. Okay. There are several other tests. For the Shapiro-Wilk, this is how it is. It's defined as this, okay, where the sample data has been sorted, and then the AI are the constants to be evaluated. Well, the R software is able to calculate that easily for you. To do that, you need to use the library car, install that package, run this for the plot. The good thing about this plot is that it will check if the residuals are normal. And you're going to see that very soon. Okay. It will check clearly. And you can also split some of the plots so that it doesn't take much of your space. So this is a plot of the residuals you get. You can see that The actual normality is the dotted lines, and our own data is the one around the dotted lines. Observation number 24 seems to be far away. It's been flagged as a potential problem child. Observation number 24 is still here. Observation 34 is also flagged. In the scale allocation, observation 24 is flagged again. In the residual versus the leverage plot, observation 25, this measures the Cook distance. Observation 24 has been flagged again. So at least it helps you to know whether the residuals are normally distributed and which observation might be a problem. It's not really a problem for this one, but if it's saying this is the QQ plot, okay, is again observation 24 and 34 appears to be flagged. So you may choose to alter these particular observations by removing them and running the model again to see. Okay, but this is our Shapiro test, which confirms everything. If the p-value is greater than the alpha, then the residuals are normally distributed. In our case, the p-value is 0.2%. So what would you say? Would you say our residuals are normally distributed or they are not normally distributed? Are they normal or not, Shaman?
They are not normally distributed.
Exactly. So it appears that one of the assumptions of normality necessary for OLS regression has been violated. Okay. So that is one thing to take note. There's another way you can test for normality using a package known as OLS-RL. This will check again for the normality case. And when you check, it will tell you that it's not normally distributed. But here's the thing. You don't have to be scared or not if the thing is not normally distributed. Normality of residuals is only needed for valid hypothesis testing. The normality assumption itself, assures that the p-value of the F statistics and the test statistics are valid. Okay. So the OLS approach we are using, it merely requires that the residuals be independently and identically distributed. Okay. It doesn't necessarily mean that by force they have to be normally distributed. And if you have outliers, especially for small data, it can bring about non-normality. It can make the thing not to be normally distributed, which would then lead to misspecification data. But suppose you've used all the plots, you've used all of these things, to check the normality. What you got to do, sometimes you just live with it. It's not a big problem, just as we've indicated. And there's an easy way you can correct for that. One way you can correct for that, if there's a lot of clear non-normality, then you can use this by running the OLS by correcting for the standard errors. This is very important to me. So you use an OLS corrected standard errors known as heteroscedastic autocorrelated consistent, corrected. Now, it will correct for both heteroscedasticity and autocorrelation in the model. But we are not talking about autocorrelation yet. So you can run the heteroscedastic corrected covariance matrix. The covariance matrix starts from 0 all the way to 7. Okay, you can run each one of them one by one and to see. You can also use bootstrapping. You can incorporate bootstrapping so that the efficiency, the beta parameters, which will have its confidence intervals. Okay, you can generate bootstrapped betas, bootstrapped estimates, and this estimate is what you can talk about them, which have been caged from sampling variations. And so you can use that to indicate that, that I used this one because I wanted to correct for heteroscedasticity. You can also use things like trimming and winsorizing okay, which leads to robust regression. You can use data transformation. Instead of using the quantity demanded, you can rather do the log of quantity demanded. We can come to this later on, okay? And that will solve a lot of other problems, not only even heteroscedasticity, it will solve other problems. Sometimes some of the independent variables, instead of just putting the variable as price, you may have to take the log of the price. Instead of dealing with C, complement price, you may have to take the square of C, okay? You have to take exponent and hyperbolic function. You can do several things, possible things, just to handle what? Heteroscedasticity. Let's take an example, okay? We'll use an example later. But before that, let's look at another thing to check. So remember, first you've spoken about checking for normality, checking for the errors being, expected value of the errors being 0, checking for normality, checking for linearity. Okay. Now let's look at the linearity. Suppose you have built this model. Y cap is equal to beta naught and then all the necessary things. You have fit this model on a data set, okay? But then the data set, this is the fitted model. This is the one you fit. But this is the model you built. The one above is what you built, and one below is what you fitted. So what you fitted, you can see that it's fractional, and therefore it's non-linear. So let's calculate the residuals from the second one. Okay, when you calculate the residuals, you're going to get something like that, which is non-linear still. So the residual plot will show a curve, non-linear. It will not show a line, which is linear. Okay, so the residuals now become what? Non-linear. How do you correct that? Well, first we need to check whether that's true. So you can use multiple things in R to correct for that. You can use component residual plot. They are very good to check if the predictors have a linear link. In fact, I'll show you that soon. Okay, it will plot the residuals and the fitted values and will ensure that the residuals don't form a strong pattern. Once it forms a strong pattern, we have an issue of not just non-linearity, but also heteroscedasticity. You can use other graphs to exhibit nonlinear. So look at this carefully. So this is the relationship between each independent variable and then the residual. So look at the first one. The first one is price. Okay, we want all of them to look like the red line. That's the whole idea. For them to exhibit linearity, we want them to look like the red line. Which of these properly matches the red line? Which of these? I know, but I hope my knowledge agrees with yours. Which of these properly fit the data like the red line? As for the dummy variables, forget about them. Which variable? Miriam.
Complement price. Complement. See?
What?
The second graph, that's complement.
Complement price, exactly. Complement price better fits the model. Okay. Now, if you check carefully, you can see that the dummies were not really important because, again, they are dummies. So it means that this is just a picture looking at the matter. It's not a guaranteed. Okay. Now, you can still check for linearity using also the residual plot instead of the component plot. And this is a residual plot. And this one focused on just the numerical variables. Because as you can see, the other one, what he was giving us was not what we're trying to even show. So this one too, fortunately or unfortunately, what does it show to you? Which one is likely to exhibit non-linearity? Which one? Which one mostly exhibits linearity? Shaman.
Price.
What is 5?
Price.
Price. Price is down what?
It shows linearity as compared to complement price and income.
Okay. All right. That's it. Okay. So here's the thing. If there is some pattern in the fitted values and the residuals, in other words, the residuals are not randomly distributed, you can fix that by applying a log transformation on the dependent variable. And that is what we are going to do. So clearly, you can see that some of them are exhibiting quadratic nature, okay, which is not linear. So we can do something about it and rerun this graph again. This is what you can do. You can take the log here. So the quantity demanded, instead of running that alone, you can rather do a log of the quantity demanded. So here I do $G log of the quantity demand. So what it's saying is that take the log on the right-hand side, you are taking the log, you are creating the log of the quantity demanded. Then we now run the model. We are just calling the model log linear model because we've taken the log. And just the Q is what we have taken the log. All the other variables are the way they are. And then you show the summary of the results. You're going to see something. Then you come back and check the component plot. And when you check it, you would notice that no pattern in the residuals versus a fitted plot are exhibited. And we've already said that if there is some pattern, okay, then the residuals are not normally randomly distributed, so we can fix that. And this is it. So now let's look at it. Do you recognize that it appears that they are more in line now than it was before? Do you see that?
Yes, boss.
Yeah. If you compare this one with the first one we showed, the first one, it looks like only complement price was looking more linear. But now you can see that even price is looking more linear. Assistance. So taking the log, that's correct some things. Okay. The other things you can check before, we can check. I'm not going to focus too much on this. I'll jump it. You can check for outliers and check for influences. I've given you some link for you to check it. Outliers and influences, they have some slight differences. You should know the difference between an outlier and an influencer. I did this thing some time ago with you. Okay. But all of this will indicate outliers and influences, outliers and influences, outliers and influences, outliers and influences, outliers and influences. Okay. And then how you handle them, Like I said, I'm not so keen on that. There's one command in R that you can use to ask it to tell you whether there's a problem with anything. And this command is known as, it's called a global regression test. It's known as the GVLMA. This command will give you a complete diagnosis. So as you can see down here, it will check for the skewness, the kurtosis, the linearity, and the heteroscedasticity. So you can see that here, the linking function, it tells you that it's not satisfied. Heteroscedasticity tells you that that assumption is acceptable. It also tells you that the global statistics assumption is not satisfied. So it's able to give you some few things for you to. So the global statistics, the one that says it's checking for whether the 10 is linear or is not linear. But in that one, it shows clearly there's non-linearity, which means you have to take the log or you have to take the square. All the others have been explained. My interest more is to look at heteroscedasticity, because I have a question also there. Heteroscedasticity. What is that? Well, let me just warm you up. The errors are called residuals. When you run a regression model, the actual value is what you see down here. Let's say quantity demanded of gene bitters for a particular shop. The fitted value or the predicted value is what is on the line. So the gap between the fitted and the actual is the residual. Now, you got to know whether these residuals are heteroscedastic or homoscedastic. What does it mean to say that they are heteroskedastic or homoskedastic? Well, let's take, for example, the fitted home price that you are seeing here. You can see that there is some sort of a pattern that is being shown on the first one. Another pattern is detected on the, and the way you know the pattern is there is by drawing that red line. And then finally, there is also a predicted home price for the last one. There is, by just plotting the residuals, you are able to detect some level of pattern. This is another one. Okay, the zigzag will tell you whether there appears to be a pattern or there appears to be no pattern in there. We are about to explain heteroskedasticity, so pay attention. It's the longest word ever used in the econometric industry. Heteroskedasticity. This is a multiple regression model. It's a general model. Heteroskedasticity comes from the two Greek words hetero, different, skedastic, spread. Like I said, it's the longest word in econometrics. It says that the variance of the error term given the independent variables is not constant. It shows that the error variances vary across observations. And heteroskedasticity can happen because you didn't collect some variables that you're supposed to collect. Because you misspecified the model, or you did not transform the data and allowed outliers and influences in your data. That's why you are suffering. So how do you check whether it's there? Well, first of all, you check for homoskedasticity. And when there is no heteroskedasticity, there is homoskedasticity, you will be able to detect that. You will see you have some lovely results for the OLS regression. But when heteroskedasticity is there, even though the OLS estimators are still linear, consistent, unbiased, the R square is not valid anymore. It's no longer best. It's no longer blue. It's no longer best linear unbiased estimator. It's not best. It doesn't have a minimum variance. Hence the blue, which means best linear unbiased estimator is no longer valid. The variances are no longer valid. The standard errors are no longer valid, even though the p-value, even though the beta values will remain the same. And a typical example is here. Suppose you model household consumption based on income X1. You will find that the variability in the consumption increases as income increases. So when you're actually dealing with heteroskedasticity, it's important to recognize the danger you are facing. So how do you check it? Well, it's never been a reason for you to throw away a good model. Mankio has said that, it doesn't mean that you should throw away your value. You can use residual plots to check, just as we did. You just want the residuals to be unbiased, to have a zero mean. And anything vertical strip or rectangle in the strip, okay, you simply want the residuals to be homoskedastic. So I have some questions for you. This one is showing, but the previous one, it wasn't sure. I'll rather ask you. So look at this first one. It is unbiased. So the beta part, the errors are unbiased, which means the errors are good. They converge towards the true value. That's what it means. And then the same errors are homoskedastic. Homoskedastic, because you can see that you are able to identify a sort of a pattern. A pattern that is constant all through. So if it is that, if I draw a line, you see that that line is constant all through in this pattern and this pattern. Even in the C, which was a little bit tricky, even in the C, there is that homoscedasticity. But you can see that for the case of C and B, they are biased. You can't really tell exactly the biasness. Can't. But you can tell graphically the homoscedasticity. When you look at all the ones down there, they are all heteroscedastic. They appears, you don't even know where they are going. There is that sort of infinity behavior. And those two are examples of that. So what is each one of the plot is saying, that is exactly what I've indicated here. So how do you check for heteroscedasticity? Graphically, we've seen it. Well, this is how you check it for. Use these curves. When you show this one in 2 by 2, okay, you can now use this plot and it will plot the whole data set. In our case, we've seen this before. And that will tell you that it is exhibiting this problem or not. Now, I told you how do you check graphically, but now how do you check mathematically? There are several tests you can use. I want you to tell me which of these tests you have used before in your life. Glasser, Harvey Godfrey, Goldfeld and Kwong. One of the popular ones are the first and the last ones. Okay. I'll not go through the details of them much with you, okay? But you're going to see very soon that these will tell you whether there is heteroscedasticity present or there is none present. There is Bridge-Pagan, there is White. These two are also very important. Bassett is fine, but it's not that popular. The main thing is to formulate the null. Remember, any test, you formulate the null and alternative hypothesis. The null will always say that the residuals are homoscedastic. The alternative will say that no, they are not homoscedastic. At least one of the residuals is not 0. One is not 0. And that makes it almost heteroscedastic. How do you make your decision? First, you find the test statistic. Okay. And if the test statistic, which is the LM test, is greater than the chi-square distributed critical value, you reject the null hypothesis of homoscedasticity and conclude that a significant evidence of heteroscedasticity exists in the model. Remember, if the test statistic exceeds the critical value, is that I'm saying that if the p-value is less than alpha, again, there is hetero. There's hetero. So you simply want a lower p-value. I mean, if you want homoscedasticity, you want a higher p-value. Because when there's a smaller p-value, you are dealing with hetero. You can use the graph and you can use the Bridge-Pagan test. So this is the Bridge-Pagan test we used. And you can see the p-value there. I ran this command, you can do it later. I ran this command and you can see that it's almost 0. The p-value is almost 0. Which then means that heteroscedasticity is present in our Brukutu data set. Which means you can't even rely on the standard errors. We also decided to test this using the Goldfeld and Kwong test. And this is another interesting result. All of these tests are here. But there are several tests that you can use. I'm just showing you as many of them as possible. When you use the problem and you identify that heteroscedasticity is there, we've already said that it can be there because of multi-co, it can be there because of nonlinearity, it can be there because of omitted variables, and so forth. So how do you correct heteroscedasticity? 3 means. Remember, we checked graphically, we've checked mathematically. How do you correct it? Number 1, transform the data. We've seen it before. If it is linear, if it's not linear, make it linear. If it's linear, make it log linear. Use weighted least square, use generalized least square, use feasible generalized least square. Or stop all this and go and run a white or robust standard error test. That is the same as a consistent heteroscedastic test. So let's take them one by one. First, transform the data. How do you transform the data? You can transform it using the log. So in all the models you have, watch the different means of transforming the data. The first one, I transform only the kill. Everything else in the independent frame is the same. This is known as log level. Log here means the dependent variable. Level means that the independent variables have remained as it was, leveled. Number two, you can rather take the log of this and take the log of one of the independent variables. And that is known as log level log. Log level log. Or you can take the log of all of them, where you have log log. Log log. Log log. When I decide to run each one of these one by one, I get the following. So first of all, let's look at the original one. Okay. So the original one will give us these results. You run it, you still get heteroscedastic. You get heteroscedastic, as you know. Okay. So this first one, you can see that I'm running the log level log. Of course, you can run the log level first. But here I'm running the level log. Okay, the level log. In other words, I'm just leveling the independent variable. I'm not even considering the dependent variable. So you can see that here, I just did the kill. Yeah, I should have run these things for you to see, but I just did a kill. Okay, the kill is still in levels, but then the P is logged. And then I show the results. Okay, for that one. You are showing the results, you are checking the R square. So that's why I can see that I have the R square and the adjusted R square to check. And when you check, you see that the heteroscedasticity is still present. This is another one. Where is that? This is one where you create the log for the kill. And you create the log for the P. And now you see this one here, you do log log. Log log. So you take the log of the kill and take the log of the P. Everything else remains the same. And then you see the results. Once again, you check the results against the previous. Or what results are you checking? Is R square. Is adjusted R square. Then this time you can see that here, I have rather taken the log of the dependent variable, the log of the price, and the log of C. So it becomes logging all. Log everything. Now you can see that I did not take the log of the dummy variables. I even took the log of the income. So everything has been logged. All of this, you want a very high R score. That's what you want. And then you compare your models to determine which one is the best. That's how you, that's how you do get that. Okay. The next thing, you remember that we said that there are three approaches to solving. So that's how the transformation approaches. The second approach is that you don't transform it, but you run a robust model. And this model is known as white heteroscedasticity corrected standard error. That's what you run. That is the one you run. The good thing, the bad thing is that your data has to be many large variables before you can actually see the effect of this. But the key point is that it will generate new standard errors, and you can use this new standard error, also called Ika-Huber white, instead of just white. Okay, and these ones will correct for the thing. In practice, we do not test for the heteroscedasticity, but directly we are reporting them. You report them, but you don't really have them. But I like this because I've used this thing to write a paper before, and this is one of the best ones to deal with heteroscedasticity. What else? Well, Another is to use the newer West. It's the best of all. The newer West is an extension of the white test or the white heteroscedasticity. It will extend it and not only correct for heteroscedasticity, but also correct for autocorrelation. It, strictly speaking, is valid in big samples. If you have only 15 to 20 observations, maybe it might not work properly for you. So these are ways to correct for what? Heteroscedasticity, where you don't transform, but you just use correction to the model. So these are the corrections. And the previous one was for the hetero, but now this robust newer West is for the both hetero and auto. Now, the last one, how do you correct it? The last one is for using not OLS again, but using weighted least square, WLS. One thing I can just tell is that the WLS, which is also called the feasible JLS, all of them are still a bit of manipulation of the original model. And then using that manipulated situation to solve for this. So first you estimate, so the WLS, the weighted least square, you estimate a transform model where all the variables of the constant are multiplied by a certain value, like this. You multiply through by a certain value, you get a new value, which is now Y. It's just like the OLS, but it's starred to differentiate it. Okay, that model is, this model is going to be homoscedastic no matter what. Okay, and that is why it is important. But it has a sister, okay, and the sister is known as GLS. GLS. If you can remember, the OLS estimator is this. We derive this variance covariance matrix. It will also come in exams. We derive this variance and covariance matrix in the OLS last time. In terms of the GLS, this is variance covariance matrix, but you are using omega in between them. And the omega is actually the corrected variance covariance matrix. You know, that is it. And that one is unbiased and consistent, unlike the OLS, which has issues of unbiasedness, issues of biasness, and issues of inconsistency. So you can do the WLS or you can do the GLS. And the advanced form of the GLS is a feasible GLS. Okay. If the structure of the model is known, then you use a feasible GLS. If not, you use a weighted least square or WLS. So here, again, I ran it in R for you to see. How do you do it? First, you estimate the model using the weight, 1 over the constant complement price. That's what I did. So I'm creating a weight. And the weight is 1 over the square root of the complement price. After multiplying all the independent variables plus the constant by 1 over square root of C. So you first have to do that. It will do it for you. You are just commanding it. Then you now create a model called WLS. You run the same thing as you did in the OLS. But watch it. At the end, you have incorporated weight equals to 1 over C. And then you've commanded R to give you the results. And the results you get, I'm telling you, is going to be beautiful. When you run the results, you're going to get some beautiful results in there. And you'll see that some of the variables that were not significant are even significant. So you correct the issue. Emily.
Now, please, how do you choose the weight?
You choose the weight randomly. You see, I chose C for the complement price. You can do P, you can do M, okay, but you use those that are numeric. You use those, any one of them, one at a time, and then you check the results to see whether there is still a problem of heteroscedasticity. If all of them give you the same results, you just choose one. But if some don't, they are the ones you are not going to use. You are not going to use that particular weight. Okay. And then, of course, you can run your overall result. You can use another weight, which is 1 over HH hat. Okay. And watch it here. So I've changed it. So here, what I'm using is I'm using the fitted value. the fitted value, that value from which you got the residuals. So watch it. The residuals are equal to this. The residuals are equal to the actual minus the predicted, okay, or the fitted. Now it is this fitted, that's the one you are using. That's the one you are using to replace that. And that will give you the feasible GLS. Okay, but then the GLS itself, or the WLS, that one will rather require you to use one of the independent factors. But then the feasible GLS is requiring you to use only the Y hat. So if you like to use the feasible GLS, is that if you have to use a weighted, let's say, estimate, and then you run your model, and then you get some significant results, and then you check and choose the one that has got the most significant estimate. So all the others, I've run them one by one, one by one. Okay. If you run them, you see that some of them are giving significant results. Some will give more significant results, you know. But this one, I'm going to put all of them together. Okay. The last one here is the newer West. So I use Stargazer to combine all of them here and now see the results for each one of them. See, when you check here carefully, you see that not all of the original model is this. Okay, so it has it. But then some of them use log, if you can remember. Those are the ones that are the log family. Okay, you have them all. So you have multiple models here, and now you can now use the coefficient to check. But look at the last one, the last column here. So that last column for me is critical. Why? Because if we check all these, they are showing some significant values. But if you check OLS and GLS, they don't show significant values for income. Check it. But then you can see that the newer West, the last one, the robust standard error one, shows significant answers. Okay. In fact, the feasible GLS is also very good, as you can see. That one is also showing significant values all through. Apart from the newer West. And when you check for even location urban, okay, you will notice that the feasible GLS is showing significant result. But you have to be careful when you're interpreting this feasible GLS. And our own also gives you significant. Now, there's something I've just observed. Between the last column, which is the newer West standard error, also called robust, and then the feasible GLS, which one would you have selected? And I want to see the smartest among you. Which one? Of course, one of them would be the best model. But which one? It's tricky, but it's tricky. None of you have seen it. Okay, I'll give it to you as a discussion assignment. You check it. One of them stands tall. Okay. So one last point, and then we'll wrap up. Under the feasible GLS, it becomes H cap. I've indicated that be careful when interpreting the result. I think I said it before, because the slope coefficient had to be explained in connection with the weight intercept that was added. Okay. So when you're interpreting it, just be careful. Instead of the feasible GLS, and it's difficult in interpretation, we can always use the newer West, you know, which then solves all of the problem, and this interpretation is also fine. Okay. And finally on this, you can see, okay, so this is autocorrelation. Okay. Autocorrelation. Look at that one the next time. But I just want you to understand three things, just three things. Heteroscedasticity, how do you detect it, and how do you solve it, and how do you interpret it? How do you detect it? How do you solve it? How do you interpret it? Understand that, because most of the papers did not correct for that. And most of them did not correct for even the ones that we'll look at next time on Wednesday. Ladies and gentlemen, that brings us to the end of the entire Kabuda. For you to be able to appreciate this very well, I will encourage you to run the whole model, and then you can appreciate exactly what we have done. Any question? I know that some of you tend to ask questions when we are going. All right. If there's none, I wish you all the very best, and I'll see you on Wednesday.